Now let's take a look at case number 4. Again, each of our cases has just told us something new that we can observe occurring in the denominator of our fraction. Here we're going to see that we're still going to be dealing with irreducible quadratics, but now we're going to allow them to be repeated. This is actually going to be extremely similar, maybe even near identical to what we did when we had repeated linear factors. Let's see what this has. I can say that if ax squared plus bx plus c to the nth power is a factor in the denominator of our fraction, and ax squared plus bx plus c is irreducible, then the partial fractions corresponding to this factor are, and again, I'm going to have a bunch of them. If this was this quadratic to the 10th power, I would have 10 separate fractions. If it's to the nth power, I'm going to start at fraction 1 and keep adding up until I hit n fractions. The basic structure of these fractions is again going to be that ax squared plus bx plus c raised to different powers every time, starting at power 1 and increasing to power n. In the numerator, I'm going to have things of a linear form. The numbers might keep changing up there, but I'll ultimately have the same linear structure. Now again, this can seem rather confusing when worded this way, but take a look at how it plays out in example 6. Notice example 6 doesn't have an integral, it's just saying, can I find the partial fractions of what I have here? So I'm only going to focus on the algebra right now. Well, take a look again at the denominator. I'll start by saying we see that, well, in this denominator here, I have a irreducible quadratic, an x squared plus a 1. But that's occurring down there multiple times, right? It's down there twice. So according to what I have up above in case 4, I should get as many fractions as there is this power. So since this is 2, I get 2 fractions. If it was 5, I would have had 5 fractions. And each fraction has a denominator of x squared plus 1 raised to different powers, starting at power 1 and going up until I hit the power that was originally down there. In the numerator, I'm going to have linear structure. So like an ax plus b, maybe a cx plus d. Okay, great. So these are 2 fractions that when added together could produce this. But I don't know what the values of a, b, and c, and d are in order to make this happen. So again, we'll get our common denominator, and we want to match the denominator that was occurring over here. Notice, what does that mean I'd have to multiply my first fraction by if I want to make this the denominator over here? Well, I'd have to multiply ax plus b by my x squared plus 1, and that's it. Because when I multiply x squared plus 1 to the top and bottom, I get a value squared. Notice then, I don't actually have to multiply by anything on that second fraction because it already would have a common denominator. So now my denominators match. And if 2 fractions are supposed to be equal and they have the same denominator, well, like we've seen before, that means that we would need to have their numerators match. So I can go ahead and write this down. Since I've been dealing, though, again here with these irreducible quadratic factors, we saw in the last video that it would be helpful to, instead of plugging in values for x, to try to think about comparing how many x's and x squareds and constants were on either side of this equal sign. So to do that, I'm going to start doing some distributing down here. So I'm going to do like ax times my x squared, ax times 1, b times x squared, b times 1, cx plus d. I want to write it out like this so again I can compare how many x's, x squareds, and on are on each side. I know they need to match. So if I write this side in descending order, I see that I have ax cubes, I have b x squareds, I have a plus c x's, and then I finally just have like b plus d as a constant at the back. From here I can generate a nice system. I can see that if the number of x cubes on both sides are going to match, I have 0 x cubes on the left, a of them on the right. I have 1x squared on the left, b of them on the right. I have 1x on the left. I have a plus c of them on the right. And I have a constant of 1 on the left. I have a constant of b plus d on the right. This again forms a system, and it's a rather simple one. 2 of the values are already solved for. In other worksheet questions and in other assessments, these systems may not always be this easy. I just don't want to get hung up on solving each of these systems at the moment. But notice that from here it's pretty easy to deduce that if a is a 0, c has to be equal to a 1, and if b is a 1, d has to be equal to a 0. So we can actually quickly solve for all these values, and then we know that x squared plus x plus 1 over x squared plus 1 all squared actually does turn into a plus bx, or sorry, ax plus b, excuse me. So that's 0 x's plus 1, or I could just write that as 1 over my, let me shift this over a little bit just for more space, sorry, but I'm going to have a 1 over my x squared plus 1 all to the first, and then I'm going to have 1x plus 0, or just x, over my x squared plus 1 all squared. So if I wanted to do integration, instead of integrating this fraction, I know I could instead integrate those two. Now, I'm not going to go ahead and do the integration here since the question didn't ask for it, but you could probably go ahead and spend some time on your own thinking about how you would integrate each of these. One of these, very surprisingly, is actually a derivative rule that you know from Calc 1. I'll leave it to you to figure out what that is. Please make sure that you're going ahead and practicing these sorts of questions with the worksheets that we have so you can make sure that you are very well prepared to tackle questions like these when it comes time for the exam.